Okay, so this is vectors part 2. So vectors. And we can just call it part 2 if we want to. That's fine. It doesn't matter. Now, last time I talked about vectors in a line, or linear vectors, and we said how we add them together. In that case, we do vector 1 here. We could call it A or B or 1 or whatever. It doesn't make a difference. And then we can take vector 2 and just add it together onto there, head to tail. And head to tail is the key. Okay. And what we end up with our resultant, which is the total length. Okay. So this was just regular vector addition. So that's vector 1 and vector 2. And we put the little symbols for vectors on the top of them, and then we add them together. 1 plus 2 equals r. Okay. And this vector, this is 1, 2, 3, 4, 5, 6, 7. And we're adding it to 1, 2, 3, 4, 5. So we end up with our resultant is 12. Okay, anyway, that's a little bit of a quick review for it. So what we're going to do now is we're going to be talking about not vectors that are linear, but rather vectors that are at angles. So this is going to be sort of a tiny bit on the tricky part. Remember, if we have a vector at an angle, it's at an angle with respect to an axis. And usually we're dealing with the x-axis or we're dealing with the y-axis. Okay, so we can have an angle that's here, so we'll call it that angle right there, or we can call it the other angle on the other side. But this angle right here, we're just going to label it as theta. Okay, or as I said before, we can call it theta. So here, and theta is a usual Greek number that we use, Greek letter that we use. It just means that it's the angle that we're going to be using. We can use other Greek letters, and other Greek letters are used quite often. Alpha, beta, gamma, phi, but theta is probably the most well used of the Greek letters for this. Okay, so what we're going to be talking about here is still some vector math. This vector here that is off at an angle, and as I showed you before, let's just say that this is going from this point here, and it is going up to we'll go up to there. So we're going a little longer than the one that we had done in the first place. Okay, and we have some angle that we have here, which is theta, like I said. So this is our angle theta, and actually my arrowhead should probably be the other way. If we're coming from the x-axis and sweeping it out this way, it shouldn't be an arrowhead right there. We should actually have the arrowhead on the other side. But that's okay for right now. So what we can do is we can break apart our vector here, and let me call this one, I'll just call it vector A. So here's vector A. And vector A I'm going to break apart into the parts that are along the axes. And here is one part here, which is this one that goes along the x-axis. And because it's along the x-axis, I'm going to label it or call it A sub x. And then I'm going to break it into the y-axis, which is this one right there, and we're going to call this A sub y. So the big thing that should pop out into your head here is the shape. What shape did I just make? And this shape is, of course, a right triangle. And right triangles are the easiest ones to solve for. So by using the axes, we have created and I totally misspelled created a right triangle. Okay, and right triangles are very easy to deal with. Okay, so remember the Pythagorean Theorem. Okay, so a squared plus b squared equals c squared. It's the Pythagorean Theorem, and it's something that you guys should have learned already in the past. Okay, but in this case, it's going to be a x squared plus a y squared equals a squared. That's what this particular one is telling us. So to find a, it's going to be a x squared plus a y squared, and we're going to take the square root of that. So here we have some angle theta that we're not really going to concern ourselves just yet. So with this, I'm going to place in here to figure out what our a is. A is going to be equal to, and I can count these because I'm using a graphical representation of these lines. It's on graph paper, so these numbers I can count the number of squares here, and I can count the number of squares up here, and these numbers of squares are going to give me a pretty accurate count because I'm just saying that each square is a unit. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to go 10 here. So a is equal to 10, or sorry, ax is equal to 10. Ay is equal to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've got 10 and 8. So now I can place it in here to figure out what a is. A equals 10 squared plus 8 squared, and then I take my square root of that. And with this class, we are going to end up using our calculators. So with our calculator in hand, we're going to go ahead and do this. Now, it depends on the type of calculator you have, and how many lines you have on your calculator. This one that I'm showing you right here is a graphing calculator, so I can do everything all at once. So I can place it in like this. I put in my square root sign, I do a parentheses, and I do 10 squared plus 8 squared. Then I close my parentheses. It's going to do the square root portion of it, and then I sit here and hit equals, and I end up with a is equal to 12.8. Okay, the rest of the numbers I don't care about. The rest of the numbers are what we call insignificant. Okay, we want to keep it to a decent number of digits. Okay, so the length of A then is 12.8. So this one's 10, this one was 8, and this is 12.8. The hypotenuse here should always be, on a right triangle, the hypotenuse should always be longer than all of the rest of the sides. Okay, not put together, just it should be longer than the rest of the sides that are there. Okay, so this is how we're going to break it apart. Now, in order for me to find theta, I am going to have to use trig function. Okay, so the trig function I'm going to have to use is either sine, cosine, or tangent. And we have it here, if you can remember the saying, we have so, ka, toa. Okay, so remember that sine, or so, is sine theta equals opposite divided by hypotenuse. We've got cos, or ka, which is cosine theta, equals adjacent over hypotenuse. And then we have tangent theta, which is toa. Tangent theta equals opposite over adjacent. Okay, so this is where we get the so, ka, toa. Okay? All right. So here we have all the lengths. We've got the adjacent, the opposite, and the hypotenuse. Okay, opposite is across from, adjacent is next to, and hypotenuse is the hypotenuse of the triangle. So we can use any one of these. I tend to use sine probably more than any of the others, but it could be any way that you want. So I'm going to use sine here. So sine theta is going to be equal to opposite over hypotenuse. Well, this is going to be opposite is AY over A. So my sine theta is going to be 8 divided by 12.8. That's sine theta, but that's not what I'm looking for. What I'm really looking for is what is this angle here. So theta. Theta is going to be sine inverse, sine to the -1, or arc sine, it depends on the terminology that you want to use, of 8 divided by 12.8. When I plug this into my calculator here, what I'm going to do is say second function, so the second function right here, second function sine, and then I put in my parentheses. 8 divided by 12.8, and then close my parentheses. So you can see it all right there. The sine function here is telling me that I am not looking at what sine theta is, I'm looking at theta. So I'm taking an inverse of that particular function to do this. Then I hit enter, and I get theta is 38.7 degrees. It says 38.682. I'm going to round. So theta equals 38.7 degrees. So there. Now I have my magnitude and my direction, and it's all together. So A equals 12.8 at 38.7 degrees. Okay? And that's it. That's how we solve for a single vector. Next time I'm going to talk about, well, what if we have multiple vectors and we put it in here, okay? All right.